think we can begin. Welcome, everyone. It's my pleasure to introduce Chenchen Zhao. She's from the University of Southern California. She's a graduate student there, a fifth-year graduate student. She works with Greta Panova, and she's going to be talking to us about the Kronecker and Littlewood-Richardson coefficients. And this is a background talk for the PNW Integral Probability Conference happening here at Oregon State in this Friday and Saturday. So I'm really excited to hear Chenchen Zhao give us a background talk for that in preparation for Greta's talk. Chenchen, please.
Thanks, Axel, for inviting and introducing me. So I will be talking about the Kronecker and Littlewood-Richardson coefficients today. Since this talk requires no prior knowledge on algebraic combinatorics, I'll start with the basic representation theory. So permutations are just bijections from 1 through n to 1 through n, and here is a diagram representing this permutation. So 1 goes to 4, 2 goes to 1, and 3 goes to 2, and so on. And the symmetric group is a group of those bijections under the action of composition. So for instance, if we are given two permutations, pi and omega, their product, one will be sent to 3 by omega, and then 3 will be sent to 2 by pi. And so 2 to 4 to 5, and so on. So this composition or the product is equal to the line, the permutation with the line notation 2, 5, 3, 4, 1. And representations of the symmetric group are just group homomorphisms. It will send the permutations to matrices, to invertible matrices. Yeah. we are reading from right to left. So if here, if we choose the space to be C3 or C cubed, and the permutation matrices, those are representations of the symmetric group. So 2, 3, 1 will be sent to E2, E3, and E1. And we can decompose the representations into irreducibles, and or we can decompose the space into minimal Sn invariant subspaces. So for instance, we can be decomposed into the subspace spanned by E1 plus E2 plus E3, and its orthogonal space, which is the space spanned by E1 minus E2 and E2 minus 3. So we can be written as V1 plus V2. And the irreducible modules up to isomorphism of the symmetric group are the spec modules. And these modules are indexed by the integer partitions. Integer partitions here, if a lambda has a length of L, then it's just a L consecutive weakly decreasing positive integers, and they sum up to n. So we say this is a partition of n. And we use a Young diagram to represent these integer partitions. So for instance, here is a Young diagram for the partition 6, 3, 1. We'll put 6 boxes on the first row, 3 boxes on the second row, and 1 box at the last. And the example we have above, so V1 is isomorphic to the spec module corresponding to 1 row, and V2 is isomorphic to the spec module corresponding to 1. And the basis for the spec modules are the standard Young tuple of shape lambda. So the standard Young tuple are just if we have a Young diagram, we are filling it with integers from 1 through n, and we are using each integer exactly once. So each row and column are strictly increasing. And here are some examples. So when lambda is equal to 3, there are 5 standard Young tuple we have. And when we study the representations, we don't look at the matrix directly. We look mostly we study them through characters, and the character is like the trace function. And so this characters will be the same for the elements in the same conjugacy group. And here is an example of the character table we made. So on the for each column here, we have a permutation in cycle notation. And basically for instance, for this first column, the characters are the same for any permutation of this cycle type. And so if we, for instance, if we have V2, the spec module indexed by 2, 1, and we write out the permutation, we write out the matrix, this representation will send the 3 cycle 2, 3, 1, 2 is 0, -1, 1, -1. And the character of this 3 cycle is the trace of this matrix, which is -1. So this is the definition from representation theory. And in combinatorics, we actually do have a purely combinatorial rule to compute this character. That's the Murnaghan-Nakayama rule. So the character chi lambda of permutations of cycle type alpha is equal to the sum of -1 to the height of t, where t summed over a border strip tableau of shape lambda and type alpha. And the height of t is the sum of the heights of each of this border strip minus the length of alpha. And so border strip tableaus just means, border strip tableau will have a weakly increasing row and columns. The columns doesn't have to be strictly increasing. And each border strip is the shape occupied by each integers for, and the border strip means it doesn't contain a 2 by 2 shape anywhere. And for instance, if we are computing chi21 evaluated at the 3 cycle, we are filling this tableau of shape 2, 1 with 3 ones, and there's only one way of doing this. And this border strip has a height of 2 minus 1, which is 1. So the character here is equal to -1. And if we are filling the tableau with 2 ones and 1, 2, there are 2 ways of doing this. We can either put the 2 ones on the first row or put them in the first column. And in the first case, the height is 0. And in the second case, the height is 1. So we have 1 minus 1, which is 0. So this is another way to evaluate the characters. And irreducible representations of the general linear group are wild modules. They are also indexed by partitions, but this time we have no limitations on the size of the partition. Instead, so this partitions, the only restrictions there is their length is less than or equal to n. And the Schur functions are the characters of these wild modules. And we have a wild character formula for to compute the Schur functions. So it's defined to be the determinant of this large matrix xi to the lambda j plus n minus j divided by the Vandermonde determinant. So for instance, if we are considering the staircase shape of length k minus 1, the Schur function of this this partition is equal to, we can just plug it in, lambda j will be equal to k minus j, and then we have the matrix xi to the 2 times k minus j, and this will be equal to the product of xi plus xj with I less than j, indexing over all possible values. So, and there's a combinatorial way to write out the Schur functions. So
sorry, I have a quick question.
Yeah.
So for these characters, what do the variables x1 through xn represent?
Oh, You mean in the Schur functions? So if we are evaluating at the diagonal matrix x1 through xn.
I see. Okay. All right. Thank you.
And so we can expand the Schur functions as in terms of using the semi-standard Young tableau. So each of these semi-standard Young tableau is corresponding to a monomial. For instance, here, the shape lambda is equal to 2, 1. The semi-standard Young tableau are tableaus that are not weakly increasing in row and strictly increasing in columns. And we are filling the tableaus with 1, 2, and 3 here because we are only using x up to x3. And there are 8 ways to do this. So for instance, the first one, we have 1, 1, 2, and this is corresponding to x1 squared times x2, and so on. And so we just mentioned that the basis for the spec modules, those are the standard Young tableau of shape lambda. And how do we know that if lambda is 3, 2, we have all of them? There is actually a way to compute the number of standard Young tableaus of a particular shape, and that's given by the Hook-Lance formula. So the number of standard Young tableau of shape lambda will be equal to n factorial divided by the product of the Hook-Lance at each spot. So for instance, this lambda I minus I plus lambda j prime minus j plus 1 just means the distance from the particular box to the rightmost, the horizontal rightmost box, and plus the distance from it to the vertical bottom. I can draw it here. So for instance, we are consider the length of this hook for 1 is 4. And for this 2, we are considering this hook through 2 has a length of 3. And so the denominator is just a product of all those hook lengths. And in this case, it's 5 factorial over 4 times 3 times 1 times 2 times 1. And for the semi-standard Young tableau, we have a similar formula. And again, the denominator is divided by the hook length, and on the top we have n plus j minus I. So this could be obtained by evaluating the Schur function at once. So each of this semi-standard Young tableau will contribute 1 to this Schur function, and then adding them up will count the number of semi-standard Young tableau of shape lambda. So the Costco number is defined to be the number of semi-standard Young tableau of shape lambda and content mu. So here M mu is the monomials corresponding to mu. That means M mu is just x1 to the mu 1, x2 to the mu 2, x3 to the mu 3, and so on. And this Costco number is positive only if the shape lambda is greater than or equal to mu in dominant order, because that's the only way we can possibly form a semi-standard Young tableau. All right, so let's now define the Kronecker coefficients. So the Kronecker coefficients is the multiplicity of the spec module in the tensor product decomposition of S lambda tensor S mu via diagonal action. And we can compute this Kronecker coefficients through the characters. And as we can see by this formula, lambda, mu, and nu, they are fully symmetric. So we can switch over the indices, the 3 parameters. And here's an example to compute it using character table. So if we are doing the tensor square of chi to 1, then we are just squaring this second row here. And we are gonna get the last row. So we are squaring 2, 0, minus 1 to obtain 4, 0, 1. And if we make some observations through this table, this 4, 0, 1 is the sum of the previous 3 rows. So this gives us a decomposition. The tensor square of the spec module 2, 1 is equal to the linear combination of S3 plus S21 plus S111. And by definition of our Kronecker coefficients, this means the Kronecker coefficients is equal to 1 for any partitions of shapes of size 3. And another thing to notice that is that since 1 to the n is the sign representation, and we have chi mu tensor by chi 1 to the n will gives us chi mu prime, where mu prime is just the conjugate partition, like we transpose it. So the Kronecker coefficients will have the transposition property. We can transpose any 2 of the 3 parameters, and it will give us the same Kronecker coefficient. And the Littlewood-Richardson coefficients are also multiplicities, and they are multiplicities of the while module in the tensor product decomposition of 2 while modules. And we actually have a combinatorial way to interpret this Littlewood-Richardson coefficients. That's by Littlewood-Richardson. So this Littlewood-Richardson coefficients, they are equal to the number of Littlewood-Richardson tableau of shape mu minus mu and type lambda. So for instance, what are the Littlewood-Richardson tableaus? There are a few rules to it. So first of all, it needs to be weakly increasing in rows and strictly increasing in columns. And plus, if you do the reverse reading word on it, that is, if you read off the tableau from right to left, top to bottom. So for instance, the words corresponding to this tableau on the left is 1, 1, 2, 1, 3, 2. So this word needs to be a lattice word. By lattice words is a word that it can never have, you cannot, for any initial sequence of this word, you will not see more I plus ones than i's. And in this case, we have nu is equal to 4, 3, 2, and mu is 2, 1, and lambda is 3, 2, 1. And there are only 2 possible Littlewood-Richardson tableau that we can come up with. So the Littlewood-Richardson coefficients is equal to 2. Any questions on this part?
Yeah, I have a question. So I see the 4, 3, 2. That's like if you were to fill in the missing boxes. And then the 2, 1 is the box that you removed.
Yes.
The boxes that you removed, and then the 3, 2, 1 is.
It's the type of the tableau. So we are filling it with 3 1s, 2 2s, and 1 3. So the general shape, if you didn't remove the 2 1, we are gonna get a 4 3 2 tableau. So this shape is like 4 3 2 minus 2 1.
Okay, I see. And then the content is the 3 2 1.
Yeah.
Okay, thank you.
Okay, so next I will discuss some identities we use related to Schur function intensively in our field. So the first one is the Littlewood-Richardson rule. That just follows from the previous thing we talked about. And the next thing is the Cauchy's identity. So if we sum over all partitions, lambda, so if we sum over lambda, the product of S lambda of X times S lambda of Y is equal to the product over all indices ij, 1 over 1 minus xi times yj. And if there's a generalized Cauchy's identity that involves the Kronecker coefficients. So if this summation is over all partition triples, lambda mu nu of the same size, and g lambda mu nu times s lambda of x as mu of y as mu of z is equal to the product over ijk as 1 over 1 minus xi yjzk. And there is a classistic version of the identities. So if we are filling the parameter, if we're using instead of x, we are using xy, which is the product of x and y. So it's the contents is x1 y1 x1 y2 and x2 y1 x2 y2 and so on. And this will be equal to the sum over partitions mu and nu, the Kronecker coefficient g lambda mu nu as mu x times as mu y. We can see, so the last three equalities, they are related. So for instance, if you multiply both sides here by as lambda of z, and you sum over all lambda. So by the Cauchy's identity, you are gonna get whatever we have on the right-hand side for the generalized Cauchy's identity. So this part is for xy and the other part is for z. And next, we can actually use the generalized Cauchy's identity to derive a closed formula, an alternating formula for the Kronecker coefficients. So we start with the generalized Cauchy's identity, and recall that we have a wild character formula. Thus, by definition, this Schur function is equal to this determinant divided by the Vandermonde determinant. So if we multiply both sides of the equation by this 3 Vandermonde determinant, we're gonna have the left-hand side of the equation equal to the sum over all partition triples of the same size, the Kronecker coefficients multiplied by this 3 determinant. And so here, because we are the exponent for this matrix here, we are adding to the original partition from lambda 1 through lambda n by n minus 1 through 0. So this will make the coefficient, the exponents all different. So because we are making a weakly decreasing array to a strictly decreasing array. And therefore, this coefficients here will be equal to the coefficients corresponding to x1 lambda 1 plus n minus 1, x2 lambda 2 plus n minus 2, and we can expand it. So to find a formula for this Kronecker coefficients, it suffices to find a formula for the coefficients matching the corresponding term on the right-hand side. And we can expand it to do it. So turns out this Kronecker coefficients will be equal to this alternating sum over permutation triples. And here the C of lambda plus pi minus I is it's counting the number of 3D contingency tables. And the 3D contingency tables are, you can think about it as a cube, and you are filling in the table with some integer, some non-negative integers, so that if you slice this through, it has satisfied some marginals. So the sum of the first slice is equal to alpha 1, and the sum of the second slice is equal to alpha 2, and so on. And here's an example of computing the Kronecker coefficients using this equation. So we are just enumerate over, here we have n is equal to 2, and we are enumerated over all partition triples, and it gives us, it could be reduces to the sum. And so for the first one, if the contingency table has marginals 3, 0, 3, 0, and 3, 0, then there's only one such contingency table. We can only put the 1 at the position A111, because anything involving an index of 2 will become 0 by the and as we can see from this formula, because we're only using a very small partition and it has only a size of 2, and the contingency table involves some 6, 5, and plus minus. We cannot really tell the size of this Kronecker coefficients from this computations, because the contingency table, when we count them, they may be very large numbers, but because we are involving alternating sum, it involves some cancellations, and we cannot really tell which part will got canceled. So this is not that useful on telling us the positivity or the size of the Kronecker coefficients. And by nature, we define the Kronecker coefficients and the Littlewood-Richardson coefficients. They are defined to be the multiplicities. So they are by nature non-negative integers. And in combinatorics, when we have those kind of integers, we like to find a combinatorial interpretation. So we like to find a set of objects that these numbers may define to be the describe the size of the objects. And so for the Littlewood-Richardson coefficients, we already have that. That's come with the Littlewood-Richardson law. It counts the Littlewood-Richardson tableaus. And indeed, the Littlewood-Richardson coefficients, they are contained in the Kronecker coefficients. And this is a classical result by Murnaghan. So if we know that in the 3 partitions in the Littlewood-Richardson coefficient, they are not of the same size. But if we add a long first row of variance lines, we can make them to be of the same size. And then we use those as the partition triple for the Kronecker coefficients. In this case, the Kronecker coefficients will be equal to the Littlewood-Richardson coefficients. So, and then we would like to find a positive combinatorial interpretation for the Kronecker coefficients. So we'd like to find a set of objects that the Kronecker coefficients maybe describe the size of those set of objects, but this is a very, very difficult question, and it remains open because of the lack of tool that we can use to study the Kronecker coefficient. And I'll go through some partial results regarding this combinatorial interpretation questions. So in 1989, Remo started computing the Kronecker coefficients when we have 2 hooks, or when we have one of the partitions is a 2-row partition, the other one is a hook. And in both cases, the third one could be anything. And in 1994, Remo and Whitehead, they come up with explicit formula for, like they come up with a formula for when we have 2 2-row partitions, but again, it's like an alternating sum, and it's not very interpretable combinatorially. And in 2006, Balantin and Orellana, they come up with the combinatorial interpretation when one of the 3 partitions is the 2-row partition. This is like the very first most combinatorial interpretation we have, but it's very restricted. So the 2-row partition cannot be any 2-row partitions. It requires the first row to be a long first row. So the n minus k need to be at least as large as 2k minus 1. And in 2014, Blasiak and Ricky Liu, they found a combinatorial interpretation when one of the partition is a hook and the other partitions are arbitrary. So they come up with something called the Kronecker Tableaux that involving like coloring and and some partial ordering. But again, this does not generalize. This is just for one hook length. And there are some other special cases computed. For instance, Combinatorial and Rosas, they find the reduced Kronecker coefficients. They count the number of point partitions. And but in general, little is known about the combinatorial interpretation for this Kronecker coefficients. And because little is known about these Kronecker coefficients, basically we will consider like understanding it in any way is a good thing. It's an open problem. And so alternatively, you can study the positivity, the asymptotic behavior, and the complexity. And so we mentioned the Littlewood-Richardson coefficients. They are special cases of the Kronecker coefficients, and determine the positivity of the Littlewood-Richardson coefficients is an easy question. So Terry Tao, they in 1999, they come up with a Hive model that described the that could be applied to the Littlewood-Richardson coefficients. We can describe them as counting some integer point in of polytope, and this could be used to determine the positivity in polynomial time. There's a polynomial time algorithm to do so, but even though we determine the positivity of the Littlewood-Richardson coefficients are easy, to determine the asymptotic behaviors of them are still hard, and Greta will talk about that more in her talk. And so alternatively, we are looking at the positivity of the Kronecker coefficients. In 2002, there's a theorem by Heidi, Saxo, Tiep, and Zaleski. They proved that for a finite simple group of Lie type, every irreducible representation of this group is a constituent of the tensor square of the Steinberg representation of G. And they further make this tensor square conjecture, saying that this could be extended to the symmetric group. So the tensors, there exists some irreducible representation of the symmetric group such that the tensor square of this representation contains every irreducible representation of the symmetric group as a summand. And so in other words, this means there exists a partition such that when we do the Kronecker coefficients, G lambda lambda mu, it will be positive for all other partitions mu, or for all partitions mu. And one immediate thing from this is this lambda need to be symmetric, because if one, for instance, if the one column partition is in it, then that means lambda is equal to lambda prime for this to be positive. And in 2012, Saxo made this conjecture saying that when we have a triangular number n, this partition, a staircase shape satisfies this conjecture. So the tensor square of the staircase shape will contain every irreducible representation of the symmetric group when n is a triangular number. And there are some results on this Saxo conjecture, but again, it also remains open. So Peck, Panova, and Vallejo, they prove that when M is large, all hooks, 2-row partitions, and some partitions with 3-row or with 2-row plus a extra column, they are contained in the tensor square of the staircase shape. And in 2015, Ekenmeyer, he prove that the partitions that are dominance comparable to this staircase partition, they are the constituents. And another perspective is to raise the dimension. So in 2016, Luo and Selke, they proved that if instead of the tensor square, we do the tensor fourth power, it could be proved that it contains every irreducible representation of Sn. And actually recently, I think in June or July, Riba proved that the tensor cube of the staircase shape, it contains every irreducible representation of Sn. And so one intensively used techniques in the proof of these positivities is the semigroup property. So the semigroup property states that if we have two partition triples that gives us positive Kronecker coefficients, we can add them up horizontally, and the Kronecker coefficients we obtain is still positive. So for instance, by adding them up horizontally, we just add them row by row. And here, the left partition is a partition of 4, 3, 1, and the right one is a partition of size 6, 1, 1, 1. So we are adding the first row to the first row, so we're getting 10, 4, 1 plus 1, 2, and 1. And because we have the transposition property for the Kronecker coefficients, we can conjugate any two of the partitions and make the Kronecker coefficients stay the same. So we can conjugate any two of the horizontal sum to make it into a vertical sum. So the Kronecker, that means this also it's like the second type of the semigroup property. So we can add two partitions vertically, and the third partitions we add them horizontally. The Kronecker coefficients is still positive. And because of this property is intensively used, if we think about this, we consider the building block for this. This semigroup property is actually coming from the physics, and we didn't. I don't think we prove it from within the algebraic combinatorial scope. We find this result. The Kronecker coefficients define something in the physics, and they find this in the spectral theorem or something, and we take it to use it. And so we are looking at the building block for the semigroup property. And if we consider a rectangular shape, the only way we can decompose a rectangular shape is to decompose it into sum of rectangular shapes. And there's no other ways that we can write a rectangular partition into the sum of any other two type of partitions. So we consider the rectangular shape or the square shape the building blocks for the semigroup property. And Banserot and Panova make this conjecture that the partition that satisfy the tensor square the tensor square conjecture, the partition, they have to be self-conjugate, and their Durfee size, which is the length of the diagonal, is a list of k of n, and it's not a square partition because it's proof that the square partition has some missing partitions from the tensor square of it. And so in particular, I'm looking at the tensor square of the square partitions. And it's conjectured that the tensor square of the square partitions, they contain almost everything except for the partitions from this set S. So the set S contains two serial partitions and some hooks. And here are some positivity results along the way when people are proving positivity for the Saxo conjecture or other things. So it's been proved that the tensor square of a square shape with set length at least 7, they only misses hooks when J is from the set 1, 2, 4, 6, m squared minus 2, m squared minus 3, m squared minus 5, and m squared minus 7. So it only misses some hook and its conjugates. And in 2013, Peck and Panova showed that the tensor square of a square shape with set length at least 8, they contains all two-row partitions. And so this PK of, so you can write the tensor, you can write the Kronecker coefficients G of square m, and mu to be equal to the difference of the number of partitions in the m by m square of K. So if the second row of the two-row partitions you are looking at is K, and this could be written as this difference, and this difference is indeed positive. And here are some results I have so far. If I'm able to prove that if we have a near two-row partitions, that's if we add one block to the third row, and if we have a very small second row, then this Kronecker coefficients here will be equal to 0, 1, K is less than or equal to 4. And to prove this Kronecker coefficients is 0, we do this by direct computation. Like we use the Schur function, we expand it and extract the coefficients. And 1K is slightly larger. 1K is from 5 to n to the size of the set length. We have this closed formula for it. It's equal to the sum of L1 of alpha and minus f of K, where f of K is the number of partitions of K with no parts equal to 1 or 2, and L1 denotes the number of different parts of the partition. Yeah, but and this number could be shown to be greater than 0, 1, K is greater than 5 and less than or equal to m. And yeah, and another way to, and for the general case, if K is a longer second row, if we have any two-row partitions plus a single box on the third row, and we can prove the positivity 1K is long. And the idea is we can decompose square partitions. We can remove, we can do induction on this by adding 2 by m rectangular strip to the right and adding a 2 by m minus 2 rectangular strip to the bottom. So we can, by adding those two strips, we make it a larger triangle, and we can repeatedly apply the semigroup property to show positivity. And when the set length is an odd number, we can decompose it into 4 rectangles of roughly the same size, and again do induction on it. And another techniques we use to prove the positivity is from the theorem developed by Peck, Panova, and Vallejo in 2013. So if we have a self-conjugate partition, and we're considering the principal hooks of this partition. So the principal hooks are just the hook, the partition generated by the hook of the partition. So maybe I can draw a diagram. So for instance, So the principal hooks are the length of the outer hook. And then the second entry is the length of the second hook here. And the third entry is the length of the next hook. So using those hooks, we can see it's like a weekly, it's a strictly decreasing sequence, and it's a partition. So if the character of lambda evaluated at mu for some lambda is not 0, then this lambda will be a constant, will of the tensor square of our mu. And yeah, and we can use it to prove the positivity for this group of partitions that it's near hook partitions. We're adding a single box to the corner of the hook length. So recall that we have the Murnaghan-Nakayama rule to compute the characters. So it's the same as when we evaluate the character of this thing, we are consider the rim hook tableau of shape m squared minus k minus 2 to 1 to the k, and of weight 1, 3, 5 through 2m minus 1. So and the only ways we can arrange the rim hook of shape 1 and shape 3 are this following 3 ways. So we can discuss the height of the rim hook tableau we obtain in each of the 3 cases and add them up using Murnaghan-Nakayama rule, and this gives us the characters. And using this method, we can show the character will be non-zero for any k not in the set above. And by a similar method, we are able to prove the positivity when we add 2 boxes to the hook shape. Yeah, and that's all for my talk today. Thank you. Are there any questions?
Great, thanks. Questions? I had a question about the generalized Cauchy identity.
Mm-hmm.
I know that the typical Cauchy identity is used in terms of probability, and maybe this is something that you're not as familiar with, but for the Cauchy identity, it's used in probability to define Schur processes. Mm-hmm. And I was wondering if you're aware of any like probabilistic models that use the generalized Cauchy identity, or whether it has like a interpretation in terms of probability.
I'm not sure about that. I don't really know about probability models.
Yeah, I figure as much, but I thought I'd ask.
I can say a little bit, and this is that the Cauchy identity, this generalized Cauchy identity is inherently a 3-dimensional identity.
Uh-huh.
And as you can imagine, 3-dimensional probabilistic models are very, very hard. So basically the answer is no.
All right.
And also, yeah, so I mean, this would be something interesting to do, but I don't think we are able to get any hold of this from probabilistic point of view yet.
All right, fair enough. Thank you.
I have a question also. I'm quite curious about the semigroup property, and I'm wondering if anyone's pursuing some sort of actual combinatorial proof of it, as opposed to indeed. I just checked these physicists indeed announce a proof using the spectra of operators.
Mm-hmm. Yeah, I don't think anyone has come up with any like combinatorial proof. I think it's like we just take it from the physics proof.
Yeah, it's clear a great tool. Right, thanks.
Yeah, and it's quite a coincidence that people find that they are actually the Kronecker coefficients define the thing they are studying.
Yeah.
other questions? I had one more question about this semigroup property. So you have two type of properties with the horizontal addition and the horizontal and the vertical addition. Has anyone looked at other types of addition? And I think in particular, I have in mind like strips, adding strips instead of just doing horizontal, vertical.
What do you mean by adding strips? So
Well, in the most basic case, it's say you have a shape and I just want to add one rectangle to one of the corners.
Oh, I think that will like change everything. And if you just want to add the way we add if I want to compute something by adding a specific box, if we do the Schur expansion, we can write it as like, if we multiply the Schur function by S1 and expand it, we are gonna get a sum of several terms. So yeah.
Okay, yeah, thank you. Any other questions? All right, if there's no more questions, let's thank Chenchen one more time.
Thank you.
Thank you.
All right, great. Thanks, Chenchen.